Let us now consider a general case of situation where multiple order poles occur. So, given f of s which is P s over Q s, let s minus s 1 raised to the power of r be a factor of Q f s. In this event, we say that the pole at s equals s 1 is of order r, because this particular factor is repeated r times. Then the partial fraction expansion of f of s will have the form corresponding to the pole at s equals s 1. We can write this as k 1 1 over s minus s 1 plus k 1 2 over s minus s 1 whole squared. So, the denominator will have expanding powers of s minus s 1, and finally you have k 1 r minus 1 by s minus s 1 raised to the power of r minus 1 plus k 1 r over s minus s 1 raised to the power of r plus terms which involve other poles of f of s, plus terms which involve other poles, that is poles other than at s equal to s 1. Let me call this group of terms as r of s, because we really, our focus now is on how to calculate k 1 to k 1 r. We are not interested in the other terms. So, our discussion will center around methods of finding out k 1 1, k 1 2 or up to k 1 r. Okay. Now, taking the q from the example which we discussed just now, let me say m of s is obtained by multiplying f of s over s minus s 1 raised to the power of r. So, this is the partial fraction expansion of f of s. You multiply this by s minus s 1 raised to the power of r, then this entire group of terms will be multiplied by s minus s 1 raised to the power of r. Therefore, that will turn out to be k 1 1 times s minus s 1 raised to the power of r minus 1 plus k 1 2 raised to the power of s minus s 1 raised to the power of r minus 2 down the line, plus compared to this last two terms k 1 r minus 1 times s minus s 1 plus k 1 r plus this entire group of terms r of s multiplied by s minus s 1 raised to the power of r. That is how this m of s would look like. So, every one of these terms is multiplied by s minus s 1 raised to the power of r, and this is what the result is. Now, it is easy to see now that k 1 r is simply found out by substituting s equals s 1 in this expression, because every term vanishes except this when you substitute s equals s 1. So, when you substitute s equals s 1 in m of s, k 1 r falls out. So, k 1 r equals m of s, which is really P s over Q s multiplied by s minus s 1 raised to the power of r, with the substitution s is equal to s 1. That is quite straightforward. That is k 1 r, k 1 r. Now, to find out k 1 r minus 1, we adopt the same trick as we have used in this example. You recall, we have took the derivative of m of s with respect to s. If you do that, this term drops out, and the derivative of this is simply k 1 r minus 1, and since these are all accompanied by higher powers of s minus s 1, when you take the derivative, they still continue, s minus s 1 continues to be a factor here. Therefore, they all drop out. So, when you have got dm s over ds, if you do that and substitute s is equal to s 1, then the only term that remains is k 1 r minus 1, because k 1 r disappears, all the other terms have a factor s minus s 1. Therefore, when you substitute s is equal to s 1, that remains, that is k 1 r minus 1. Now, suppose you take the second derivative, then the previous term will come. The previous term here, you recall, it will be k 1 r minus 2 s minus s1 whole square. So, when you take the first derivative, you get 2 times s minus s1. When you take the second derivative, it will be 2 times k1 r minus 2. Therefore, you have k1 r minus 2 will be 1 upon 2 dms over ds, substitute s equal to s1. As a matter of fact, this is instead of 2, I will write as 2 factorial, because that is how it progresses. This and the previous term, when you take k1 r minus 3, you will get in the final analysis 3 factorial. That is how it goes. So, continuing this discussion, it is easy to verify. You can show that k1j is obtained as 1 over r minus j factorial. The r minus jth derivative of m of s over with respect to s, with the substitution s is equal to s1. And in fact, you get k11, that is the first term here, k11, and this is in fact called the residue of the multiple order pole at s equal to s1, k11, which is the hardest to find out. It is obtained by taking r minus 1th derivative of dr minus 1 ds. So, in principle, it is the same as what we have done in the first example worked out. Only thing is, when you have got a large number of multiple order pole, you have to take successive derivatives of this term m of s, f of s times s minus s1 raised to the power of r. That is, you knock off the term in the denominator, which is s minus s1 raised to the power of r, and the rest of the rational function you take successive derivatives and substitute at every stage s equals s1. So, you get all the terms in the partial fraction expansion starting from k1r right up to k11. k11 is the numerator of the linear factor, k1r is the numerator of the factor s minus s1 raised to the power of r. So, the principle is straightforward. You do not have to really remember these formulas, provided you know the principle that is involved. You can always figure out how it is done. You have to take the rational fraction as such, given rational fraction, multiply by s minus s1 raised to the power of r, and you get a resultant rational fraction function which is called m of s. You take successive derivatives and substitute s is equal to s1. So, the principle of finding out the partial fraction expansion when you have got multiple order poles is again a straightforward extension of what you have done in the case of simple poles. And when you have a combination of simple poles and multiple order poles, you have to use a combination of both the techniques. Simple poles is quite straightforward. Multiple order poles, you have to take successive derivatives of this factor m of s. A combination of these two has to be adopted. And in the case of complex conjugate poles, if you find the residue with respect to one complex conjugate pole, it is enough. The second, its conjugate, the residue corresponding to its conjugate is the conjugate of that residue itself. This is one way of handling this. Alternately, as the example that we worked out earlier suggested, you can combine the terms corresponding to two conjugate poles and find out, have a quadratic denominator and find out a linear factor in terms in the numerator, and associate this with terms of the type e power minus alpha t cos omega t and e power minus alpha t sin omega t. That can also be done. Otherwise, if you can leave them as linear terms and then find out the residues corresponding to the complex conjugate poles, find out the inverse Laplace transform of this, and combine these two resulting time functions, which again yields finally the same result. Consider the method of finding out the inverse Laplace transformation using the partial fraction expansion. There is another method which is the contour integration, which is more fundamental and which stems from the very definition of the inverse Laplace transformation. You recall that the inverse Laplace transformation ft is 1 over 2 pi j c minus j infinity to c plus j infinity of f of s e to the power of st ds. So, in the complex plane, you take the integration along a contour like this, c minus j infinity all the way down to c plus j infinity. Let me say this contour is gamma. So this integration is along to this. Now it's easy to evaluate the integral along a closed contour in a complex plane, because from the theory of residues, once you have integration over a closed contour, that is equal to 2 pi j times the residues of the poles inside the contour for the complex variable theory. So what one does is to close this by means of two large semicircles where r tends to infinity. Let me call this gamma 1, call this gamma 2. It turns out that if you have this integral, if you have this integral evaluated around this contour, for t less than 0 it vanishes. So integral f of s e to the power of st vanishes along this contour for t less than 0. On the other hand, if you take it along this contour gamma 2, this integral f of s e to the power of st ds vanishes for t greater than 0. So since we want to really evaluate this integral along this contour from this point to this point, but nothing is lost if you add to this contour this particular large semicircle for t less than 0 and this large semicircle for t greater than 0. So in other words, I can say this is equal to 1 over 2 pi j, evaluate the contour, closed contour gamma plus gamma 1 of f of s e to the power of st ds for t less than 0, because after all I am adding to that a quantity which is equal to 0, and this is equal to 1 over 2 pi j integral along this closed contour for ds for t greater than 0. And it turns out that as far as this contour integration is concerned, there are no poles inside because all the poles will be here. Therefore, since this closed contour does not include any poles, this turns out to be 0. And as far as this is concerned, this will be equal to the sum of the residues of poles inside the closed contour plus 2. So whatever poles you are having here, you take the residues of the poles, that will be equal to your f of t for t greater than 0. This is equal to, this is for t greater than 0, this is for t greater than 0, this is for t less than 0. So in the inverse Laplace transform, you will get f of t will be identically 0 for t less than 0 because of this, and for t greater than 0 it is equal to the sum of the residues of the poles inside this. Our discussion here had necessarily to be very cursory, because this is not the method that we use for normal evaluation of the inverse Fourier transform, inverse Laplace transformation. I'm just giving this to you for the sake of completeness, and the partial fraction expansion is so much simpler, and that takes care of most of our needs. We don't really have to do contour integration, but because this is a basic one, and this will have to be resorted to for special types of functions for which we may not know the inverse Laplace transform simply. So I included this. So we will not pursue this topic. We just mentioned that the contour integration is alternative method for finding out the inverse Laplace transformation. So far we have discussed the definition of the Laplace transformation, its properties, and also the method of finding out the inverse Laplace transformation. You would have noticed that many of the properties of the Laplace transform parallel to those that we have already studied under the Fourier transform method. And we also notice that for certain functions, the Laplace transformation and Fourier transform are quite related to each other, in the sense that if you substitute j omega for s, you get the Fourier transform from the Laplace transform. For example, you have e to the power of minus alpha t ut. The Fourier transform is 1 over j omega plus alpha. The Laplace transformation is 1 over s plus alpha. So by substituting j omega for s, you get the Fourier transform from the Laplace transformation. On the other hand, suppose we have u of t itself. The Fourier transform of this is 1 over j omega plus pi delta omega. On the other hand, the Laplace transformation is 1 over s. So here there is a discrepancy. So one would like to know under what conditions will be the Fourier transform obtained by mere substitution of j omega for s from the Laplace transformation, and under what cases will they differ. This substitution will not yield us the appropriate Fourier transform. This is the question which we would like to address. Let us consider 3 cases. A, in the Laplace transformation, the f of convergence is less than 0. Now before this, it must be clearly mentioned that whenever we compare the Laplace transform and the Fourier transform, we can do it only for the causal time functions, because the Fourier transform integrates from minus infinity to plus infinity in the time axis. So f of t has values for t less than 0. There is no reason for the Laplace transform and Fourier transform to be related to each other. So whatever comparison we can make can be done only for causal time functions. So the first case corresponds to a situation where the f of convergence is less than 0, which means that FL of S has all poles in the left half plane. Examples: e power minus alpha t ut has Laplace transform 1 over s plus alpha. Example A. B, e power minus alpha t cos omega naught t will have the Laplace transform s plus alpha over s plus alpha whole squared plus omega naught squared. That means here all the poles will be in the left half plane. In all these cases, we have this: the Fourier transform f of j omega is obtained from the Laplace transform of the corresponding function with the substitution s is equal to j omega. So we have the Fourier transform can be obtained from the Laplace transform by the mere substitution of s by j omega. Conversely, the Laplace transform is obtained from the Fourier transform by substituting s for j omega. So when the f of convergence is less than 0, Fourier transform and Laplace transform are very closely related. One is obtained from the other by substitution of s for j omega or j omega for s. Suppose I have the abscess of convergence to be greater than 0. That means there are some poles in the Laplace transformation of FL of S in the right half plane. So maybe you are having some poles here. So that means that's why the abscess of convergence is a positive number. Example of such situation will be e to the power of 2t ut will have the Laplace transform 1 over s minus 2. Now all we can say is, for such functions Fourier transform does not exist because the integral does not converge. You have f of t e to the power of minus j omega t dt. That integral cannot converge because you have an exponentially increasing time function. In such cases, Fourier transform does not exist. So there is no way in which we can relate the Laplace transform and Fourier transform. Simply Fourier transform does not exist for such functions. The third case will be when the abscess of convergence is equal to 0. That means there are poles of FL of S in the left half plane and on j omega axis. on j omega axis. The abscess of convergence is 0 because you have poles on the imaginary axis as well. Example, ut 1 over s cos omega naught t s over s squared plus omega naught squared. So all these are cases where you have poles on the imaginary axis. What do we do in such cases? The general rule is FL of s in general will have FA of s which has got all poles inside right half plane, inside left half plane, plus some poles which are on the imaginary axis. Let us say bk over s minus j omega k. So it will have bk over s minus j omega k, where k, the summation is on k. That means the Laplace transform FL of s can be thought of as the combination of the terms which correspond to poles on the imaginary axis plus terms which do not involve poles on the imaginary axis, which have all poles inside the left half plane corresponding to case A. In such situation, it can be easily visualized that the Fourier transform of this will turn out to be, by substituting j omega for this, FL j omega, FLS s is equal to j omega, plus corresponding to each one of these poles on the imaginary axis, you have got bk pi delta omega minus omega k. bk pi bk delta omega minus omega k summed on k. So it turns out that in such situations, for every pole on the imaginary axis and the corresponding residue, you have an extra delta function, and that is why when you go to u of t 1 over j omega pi delta omega, you are getting the corresponding residue here is 1, so pi delta omega you are getting. So this is what it will be. So to summarize then, whenever you have the abscess of convergence less than 0, then the Laplace transform and Fourier transform are very closely related. Substitution s equal j omega will get one, you can require one from the other. But if you have poles on the imaginary axis, you have delta functions in the Fourier transform, you don't have delta functions in the Laplace transformation. We will close this discussion of the properties of Laplace transformation at this stage, and in the next lecture we will continue with the Laplace transformation in the application of Laplace transformation technique to system analysis and circuit analysis. But now I think it's an appropriate time to break at this point and look at an exercise on the topics that we have already discussed relative to Laplace transformation. The first question is, find the Laplace transforms of the set of time functions that are given here. A, t squared e to the power of minus at ut. B, t plus 2 whole squared times u of t minus 1. So this time function really starts at t equals 1 onwards. The third function, time multiplied e to the power of minus at, t e to the power of minus at multiplied by u of t minus t, a delayed step function. So once again, this function starts from t equals capital T onwards. It's truncated for values of t less than capital T. D, e to the power of minus 5t times hyperbolic cosine cos 3t ut. We have not talked about Laplace transforms of hyperbolic functions, but you can always express them as the sum of exponential functions and then combine this with e to the power of minus 5t, and you can find the Laplace transform of that. D, e, t e to the power of minus t sin t ut. Here again, you have a combination of these factors. We have worked out examples where e to the power of minus t sin t, we found the Laplace transform, but that multiplied by t. So whenever you multiply by t, it's equivalent to taking the derivative in the transform domain. So you have to use those properties to find the Laplace transform of this. F, given that f of t has the Laplace transform of f of s, what would be the Laplace transform of another function derived from f of t in this manner, e to the power of minus bt times f of t minus b. So it's scaled by a factor b. In addition, you have multiplied it by an exponential term, e to the power of minus bt ut. Take b to be a positive number and then find this out, find the Laplace transform of this in terms of b and f of s. Then we are given the waveforms of two time functions. One is an aperiodic function. This is all the function there is for outside this range from t equals 1 second to 4 seconds it is 0. So within this interval t equals 1 to 4 it behaves in this manner. It linearly rises from 0 to 3 units and then climbs down to minus 2 steeply and then remains at minus 2 from 2 seconds to 3 seconds and then once again comes back to 0 at 4 and stays there for t greater than 4. So it is an aperiodic function described in this manner. H is a periodic function. The variation for one period 0 to t naught is prescribed as here. It starts from a and comes down to 0.8a in half a period linearly and then it jumps to minus 0.2a at this point and again increases linearly and reaches 0 at t equals t naught. So this is the basic variation in one period and using find the Laplace transform of this variation in one period and then use the property of Laplace transforms for periodic functions to find out the Laplace transform of the entire time function. As a second example, we have listed here a set of Laplace transforms. Find the time functions to which they correspond. That means find the inverse Laplace transforms of a s plus 2 over s squared plus 8s plus 15, b s plus 1 over s plus 2 whole squared times s plus 3. That means there is a repeated pole here. So you have to use the rule for finding out the residues when repeated poles are involved. C 2s squared plus s plus 1 over s times s plus 2. You observe here that the numerator has the same degree as the denominator. Therefore, apart from the factor which correspond to k1 over s plus k2 over s plus 2, you also have a constant term 2 which is the ratio of the two leading coefficients. So 2 plus some k1 over s plus k2 over s plus 2 is the partial fraction expansion of this. So corresponding for the 2, the inverse Laplace transform will be 2 delta t. So whenever the numerator degree happens to be the same as the denominator degree, you have a constant term in the partial fraction expansion and in the inverse Laplace transform you have a delta function. D, you have 4s plus 5 over s squared plus 2s plus 10. These lead to complex conjugate poles. So instead of finding out the residues of each of the complex conjugate poles, you can do it. That is one way of doing this. Other way would be to treat this as s plus a whole squared plus omega squared and then try to find out the inverse Laplace transform in terms of cosine and sine functions with an exponentially decaying amplitude. Then you have 2s plus 1 over s plus 2 times s squared plus 1 whole squared. Here you have repeated poles on the imaginary axis, slightly more complicated, but you can handle this in the same way as you have done earlier. Then f s plus 2 over s squared plus 8s plus 15 times 1 minus e to the power of minus 4s. In tackling this problem, you already know the inverse Laplace transform of s plus 2 over s squared plus 8s plus 15. So all you have to do is use this information here, because e to the power of minus 4s means whatever f of t you had obtained here is the same f of t delayed by 4 seconds is what corresponds to this. Therefore, use this information that you already obtained here to find out the f of t corresponding to this. 1 over s, 1 plus e to the power of minus s. So if you had 1 minus e to the power of minus ts, we recognize this to be the Laplace transform of periodic function of time. So all you have to do is multiply both the numerator and denominator by 1 minus e to the power of minus s. So you have 1 minus s, 1 times 1 minus e to the power of minus s by s times 1 minus e to the power of minus 2s. Therefore, you can recognize this to be the Laplace transform of some periodic function with the Laplace transform for the basic period being 1 minus e to the power of minus s over s. You can find that out. Similarly, here you have e to the power of minus pi s by s squared plus 1 e to the power of minus pi s minus 1. So if you multiply both sides, numerator and denominator by minus 1, you have 1 minus e to the power of minus pi s. So you can remove that then find out the Laplace transform of the remaining function, and once you introduce that, it becomes the Laplace transform of periodic function of time. So using all the properties that we have derived, you find the inverse Laplace transforms of all these 8 functions of S. Question number 3, you have a capacitor in a circuit, current I is the current passing the capacitor, and Vc of t is the voltage across the capacitor. Suppose to the solution of this network we found out the Laplace transform of the voltage across the capacitor Vc of s. Let it be in symbolic form A1s plus A0 over S cubed, A1s plus A0 over S cubed plus B2s squared plus B1s plus B0. That is the Laplace transform of the voltage across the capacitor. Now, using this information in terms of A and B constants, find the final value of the capacitor voltage Vc infinity. B, the initial value of the capacitor voltage, which is Vc 0 plus immediately after t equals 0. Also find out the initial value of the current I 0 plus. And lastly, find the initial value of the derivative of the current I prime 0 plus. This means this is di by dt evaluated at t equals 0 plus. So this is an application of the initial value theorem, final value theorem, and the derivative rule. All these are needed for solution of this problem. In other words, you don't have to explicitly find Vc of t. Using this initial value theorem, final value theorem, and the derivative rule, you should be able to find out all these quantities in terms of the A constants and the B constants. Question number 4, use convolution theorem to find the inverse Laplace transform of 1 over s plus 1 times s plus 2. Verify using the partial fraction expansion. So this Laplace transformation can be thought of as the product of 1 over s plus 1 times 1 over s plus 2. You can find out the time functions corresponding to these two factors, and since it is a product that is involved in the transform domain, in the time domain it is a convolution. So it is a convolution of the time functions corresponding to 1 over s plus 1 and 1 over s plus 2. Find out the corresponding time function. Now you can also find out the inverse Laplace transform using partial fraction expansion, verify using partial fraction expansion, and compare the two answers. Both of them must naturally agree. So this is an exercise in not only partial fraction expansion but also using the property of convolution. Question number 5, you are given two time functions. F of t is a pulse which lasts from 0 to 2 seconds having an amplitude 1, and g of t is an exponentially decaying time function e to the power of minus tt ut. Find ft star gt, that is the convolution of ft and gt. Both are causal time functions, both are amenable to Laplace transformation. Find this down in time domain, purely working out in time domain from the basic definition of the convolution integral, you find out ft star gt in time domain. As an alternative, verify using Laplace transform. In the second step, what you have to do is find the Laplace transform of f of t, find the Laplace transform of g of t. Since we are interested in the convolution of these two, that whatever is the result of this convolution must have for its Laplace transform f of s times g of s. So you find the Laplace transform of this, find the Laplace transform of this, both are simple to find out. Find the inverse Laplace transform, you get ft star gt. Lastly, you have the error Et of a controlled quantity in a control system has for its Laplace transform this expression E of s equals s plus 1 over s plus 1 whole square plus 4. The error Et of a controlled quantity in a control system has for its Laplace transformation E of s plus 1 over s plus 1 whole square plus 4. Without explicitly finding E of t, you don't have to find the inverse Laplace transformation of this to find E of t. Without explicitly doing that, evaluate E infinity, that the final value of this error. B, integral 0 to infinity of Et dt, the integral of that error over the period 0 to infinity. C, 0 to infinity t et dt, that is time multiplied t et dt. This you should be able to do it without actually finding out E of t using initial value theorem, the rule for integration, and so on and so forth. You can also extend this to ask you to find, I can ask you to find out integral 0 to infinity of e squared t dt, that is the integral of the square error. But that requires a convolution in the complex domain. Since we have not discussed that, we have not included that type of question. So this exercise covers the various properties of Laplace transformation that we discussed in the earlier 6 lectures. In the next lecture, we will discuss the application of the Laplace transformation technique to evaluation of transients in networks and systems.